Fantastic. Thanks very much. Good morning, everyone. For those of you who managed to make it in early after last night, thank you. Firstly, I'd like to say CSA Global is very pleased to be able to be a sponsor of this event and to see how well the event's going already this year. Great sign of the times. This is going to be a bit more of a technical talk, so there's going to be a little bit of detail in the slides, but I'm going to try and talk at a fairly high level. Firstly, I'd like to thank the team that have gone together to putting this together, and also thank Hot Chili for their permission to present one of the two case studies that I'm going to present. Now, we're not a listed company, so you don't have to sit through a qualifying statement, but a little bit of background on CSA Global. We are a global organisation, and I think we're rated as one of the highest companies in terms of providing technical reports, independent technical reports to the industry at the moment. Now, enough on that, and on to my first overly detailed slide. What I'm going to be talking about today is the implementation of geometallurgy, or you can call it 3D mineral system modelling, but it's about quantifying and classifying your ore body at the earliest possible stage to get the most value out of it throughout the mineral system life cycle, not waiting to the point where you're trying to do a feasibility study and scrambling for information. There's value in collecting the right data early. It's much cheaper to do it that way, and the impact is across a range of applications from early stage ground selection right through exploration, metallurgy, mine design, through process design and on to environmental. The big question is, can you afford not to do this? And the mistake that a lot of companies still seem to make, particularly at the junior end, is they say, I'm going to do a soils program. If I want to do multi-element geochemistry on that soils program and spectral analysis, I'm going to double the cost of the analysis of each sample. But when you look at the whole program, it's maybe 10% of the additional project cost. What you can see, those of you who are familiar with Scott Halley's work, what you can see up here is an example of a company looking at a VMS system. There's the blind deposit, looking only at copper, lead, zinc values. The anomaly in the footwall is just not there, but if you did the multi-element geochemistry at the lower level, you just cannot miss the anomaly. So if you didn't spend that little bit of extra money, you may miss exactly what you're looking for. If we take it to the next stage, now we're at the exploration drill out. We're carrying on with the same sampling techniques and technologies. We're spending that little bit more on each sample, but now it reflects only 2% of the total project cost or less. And here, we're looking at, beg your pardon, we're looking at an example on the left-hand side where we've used cheaper, low-level multi-element analysis versus ICP-MS analysis for bismuth. Detection limits are different. Here, there is no anomaly. There's known blind porphyries here, they've been drilled. Here, they stand out like a sore thumb. The exposed porphyry and the blind porphyries. Again, if we incorporate the the spectral mineralogy, we see the same patterns forming, and the combination of those two data sets give you the impetus to be able to drill these targets that you might not otherwise choose to drill. What about at the resource definition stage? Now we're seriously drilling. We're doing a lot of drilling, but the cost per unit, while it remains the same, the cumulative project cost now is a fraction of a percent. Overall, what does this do? It enables us to optimise our drilling designs. We reduce costs. We're increasing our confidence in our data. We're producing more ore with less wasted money. It improves our MRE confidence, etc., etc. And right down the bottom there, it provides an early warning at this stage of any fatal flaws and opportunities that you may not have otherwise recognised, because you've got more data and better models to base this thing on. Now, I'm going to give an example of the early stage. This is Productora's project in the coastal range in Chile. These data now go back to about 2014, but using this method, we were able to build models that identified problems with the existing geological models. It enabled us to change our exploration focus, and it led to new discoveries and eventually led to a much better outcome from the PFS and the metallurgical test work. Back in early 2013, we had a mineral system that we knew had skinny feeder pipes that blew out into a breccia-hosted copper, moly, gold system here, and the geometry was well understood. It was not so well drilled on the high wall on the eastern side, and we put a hole in here, and it still looked reasonable. Most geologists would make the link here and say, oh, well, that's pretty good, we'll put a couple of holes, maybe put a hole in in here, fill this in, close it out. But when we looked at the geochemistry in this hole, and other holes off section, it looked like there was something else going on. Whilst there wasn't grade, the geochemistry was saying this part of the ore body is dipping in a different direction. We drilled the holes, and the rest is history. This was a habanero discovery back in late 2013. This added something like 12% to the initial reserve and was part of the doubling of the first resource to the second stage resource update. So then the metallurgists come on the scene, a little bit late, probably should have been talking to them earlier, and they said, I want a representative bulk sample for this. Now, if we didn't have the multi-element geochemistry, what would happen was, most likely, the geology model would be looked at, it wouldn't be qualitatively constrained, and we'd say, okay, here's our ore in fresh rock and oxide, there's 2 bulk samples, off you go. That's representative. Well, when we look at the data, all of a sudden what we see is, here we have the potassic friable breccia. It has a whole bunch of properties, which I'm not going to read out to you, that define a domain from a mineralogical and a geometallurgical perspective. Then we have that habanero discovery I just spoke about, completely different mineralogy, completely different processing characteristics, completely different rock strengths, grindability, etc. And it has issues with clay. Then a domain, an advanced argillic domain within this deposit that has no ore, but it's in the high wall, it's full of clay, it's full of voids, it's full of water, and it's a real issue from a geotechnical perspective. So collecting all of these data along the way, we're able, before we go to the MET and geotech test work phase, able to give a heads up as to the domains that are going to be of interest that need to be tested specifically. Now, if you didn't have this information, you'd start your test work, you'd find the variability was worse than you were expecting, and you'd have to do more and more test work to try and understand what was going on with the system. So again, can you afford not to do it? At the feasibility study stage, now we're well below a fraction of a percent of the total project cost, but we've reduced the risk because our model is based on every assay, or maybe spaced every 5th assay through the entire deposit. We've got spatial representativity to a GEOmet model. We've reduced the cost in a number of different ways, not the least of which is we have a bunch of half-core remnant core that's perfectly characterised that can then be thrown in for MET test work rather than doing additional re-drilling. We've minimised the risk of rework and surprises, and we've reduced the time to get the GEOmet model out as part of either the feasibility study or whatever you're up to. What I'm going to present now is the second case study, and this is a really interesting one. This is a complex skarn at feasibility stage. This skarn it's a tin skarn. I can't mention where it is, but the interesting thing about this is 20% of the value of the skarn is in fluorite, an industrial mineral, and acid-grade fluorite concentrate is critical to the value of this deposit. The client said to us, they were really afraid of an overly complex model. We need the least complex 3D geometallurgical model we can get. But it has to be able to help us to get an indicated classification for the fluorite in the mineral resource. It has to be representative of the domains, and it has to give us enough confidence to drive the feasibility study forward, given that some of our backers, our financiers, still think this thing is marginal, and they're uncertain about where they're going to go with it. So, new client, we hadn't been working with them prior to the feasibility study. They said, we've got a great geological model, we're really confident in it. It had been well logged. The image at the top is the geological model for the site, and it was a really good observational lithological model from really competent logging geologists, but it bore no resemblance to what mattered for the metallurgists. So this is a combination of primary lithologies and weathering horizons all built into the one model. Great start, but not quantitative. What we were able to do is take the geochemistry, the spectral mineralogy, and a whole bunch of other quantitative data that we were able to add over the top or pick from the data that they already had to deliver, in the first instance, a protolith model. This is pre-alteration. This is the primary lithologies. Okay, so we had a series of lithologies here. Of interest were the mafic dikes. There's mineralisation in these things, but we were worried that they may affect processing. This enabled the classification of these dikes, some variability test work that said, actually, mafic dikes, no problem whatsoever from a processing perspective. What matters is the mineralogy. Don't worry about the detail in this diagram. Suffice to say, we can use the geochemical classification of major elements to say something about the minerals. in a system and the spatial distribution of those minerals. So we can take this sort of classification into a model. There's our outcome classification colours. Here's everything mapped onto the drill holes. Now you can see the entire system here has a mineralogy classification that is semi-quantitative for every interval. In this case, they're 4 or 5 metre composites. It still works perfectly fine. We can look at the distribution of the tin grade in this instance here with the mineralogy, and it doesn't matter what the mineralogy is, but you can see here that the tin grade is closely associated with the pinks and the purples. Okay? The pinks are a quartz topaz rich domain. Topaz, highly abrasive, quartz, quite strong. The purples are the iron skarn part of the tin, lots of magnetite. That magnetite has an impact on the gravity separation of the system. So there are things that we can say from the mineralogy that directly impart information to the metallurgists. We can also say something about the mineralogy here in terms of the clay content for the processing flow sheets, for sliming impacts, but also from a geotechnical perspective. There's a heck of a lot of really, beg your pardon, there's a heck of a lot of really slimy, puggy clays sitting in the upper part of this system, and that's going to impact pit wall geometries, etc. But, sorry, let's go back one. But this is still too complex to model. Okay, what we model and what we present to the Mets has to be mineable. So we can take that detail, understand what's driving the metallurgical outcomes, and simplify the model into a dominantly quartz topaz domain, dominantly magnetite iron domain. Both of these contain high-grade tin, and then outboard of that, a calc-silicate domain. More carbonates, slightly more clayey, and then a barren causative granite on the inside. So understand the detail, but then it's really important to simplify it back to something that is mineable and is modelable and is processable. So we take those data, and this is the step that really helps us to integrate everything. We take implicit 3D geological models that can be automatically updated. We're not manually wireframing because these are a live product through the life of the mine. Saves a lot of cost, adds a lot of value to be able to continually update these as you infill drill and so forth. Our 3 domains are modelled, so our quartz topaz plunging chute here, enveloped in the magnetite zone, 2 different processing characteristics, and then the calc-silicate skarn. What does that look like to engineers and metallurgists who want to know what it looks like in 3D, in 2D I should say? Here's our east-west or mine east-west slice through the deposit, right through the centre, highest grade in the quartz topaz, and we can see from the data that the continuity is really good in these domains. So it gives increased confidence in the MET test work, and particularly in compositing for the MET test work. We can also use these data to understand the weathering profile. And again, those of you involved in processing understand the importance of getting the weathering profile right, and it's typically done from a geologist's log of percentage weathering. If you're lucky, someone might look at a sulphur in-out boundary for this base of complete oxidation, or the top of fresh rock, whichever way you like to call it. But here, we have an issue where we have friable oxide clays with completely different processing characteristics to the intense kaolinitic smectitic clays. This stuff requires washing, affects the grade. They need to know about it for the test work. Likewise, the client and the metallurgists are not interested in where fresh rock is. They're interested in sulphide in or out because there's a sulphide flotation circuit as part of this processing circuit. So, down to some of the nitty-gritty. If I just go back for a second. Actually, no, I'll just keep forward. There were 2 key outcomes beyond just provide us with a geometallurgical model that is going to help us to understand how to create our metallurgical composites for test work, how to simplify the deposit, and how to understand what's going to go through the mill and when, what volumes of material types, etc., and when. The 2 key outcomes that they needed to know was they needed to get an indicated resource for the fluorite component. It's 20% of the value in the deposit. Up until this point, the method that they had been using, and we were involved in the resource estimation for them. So we'd flagged that there's an issue around the fluorite resource, and particularly around classification of the fluorite resource. Up until this point in time, they had been assuming that all the fluorine in the system reports to fluorite. So this top left diagram looks a bit scattered, but the key point is the y-axis is the client's estimate of fluorite grade, and we're talking about grades here up to 30-40% fluorite, okay? The x-axis is, if you take into account the stoichiometry of fluorite, fluorite requires virtually equal amounts of calcium to fluorine to make fluorite. If you don't have enough calcium, then the fluorine's reporting to another mineral. So what this was showing was that the client was overestimating the amount of fluorite systematically. This line here is the maximum amount of fluorite that you can have, and you notice that all of their estimates were on that line or higher. The reality is that they have to be on that line or lower, okay? So when you look at fluorite to calcium ratios and you compare it to XRD analyses, which are semi-quantitative, not quite as precise as the calculations, you see there's a reasonably good match, but even semi-quantitative XRD is overestimating the amount of fluoride in the system, particularly at the higher grades. We can take the chemistry and say this domain in here is dominantly fluorite. These are good estimates. Down here we've got excess fluorine to calcium. There's got to be other minerals in there. It turns out to be topaz and salleite. Salleite is 60% or more fluorine. So that's a real issue. That's why they're getting some of these values up in here. Salleite's also a contaminant in the con. So we need to know where that is, and we can map that spatially. So the pink points here can be mapped out in 3D space and say, here we have other minerals that are providing fluorine into the system. They're either going to be abrasive, like topaz, or they're going to be contaminant, like salleite, and we can map where they are in 3D space. The other problem in tin skarns, for those of you who know tin skarns, is cassiterite is good. That's what you want. That's what comes out in the gravity circuit. But stannite is a tin sulfide. It's acid soluble. It doesn't come out in the gravity circuit, and it's an issue because when you do fusion XRF, you get total tin, and you can't tell the difference between stannite and cassiterite. You may well have a problem if you don't know that ahead of your resource estimate. Here, what we were able to do, again, using a combination of the 4-acid geochemistry, which we did routinely throughout the system, and the client's fusion XRF geochemistry, we can map the relative abundance of cassiterite here in blue, which is the good high recovery mineralisation, through to stannite, which is enveloping the outside of the deposit, thankfully coincident with very low grades of tin and isn't impacting the overall tin grade in terms of recoverable tin through the plant. So this gave confidence in the tin resource estimate. The previous slide gave confidence in the fluorite resource estimate, and the 3D model and the geometallurgical model as a whole gave significant confidence in the MET test work program and the feasibility study going forward. So I guess the takeaway messages here in terms of geometallurgy is it's not difficult, okay? It's most effective when it's done early, when you are careful about selecting the sorts of data that you collect, but the data is quantitative. It gives you high-value exploration outcomes that are sometimes not even understood. It saves you time and money throughout the project life cycle. As I said, the spatial representativity and confidence in the models is an order of magnitude better than putting 3 or 4 met holes in and hoping that they're representative. It provides early warning of threats and opportunities, and it reduces the risk by minimising errors and rework. The final 2 lines here are comments from this client around the tin skarn. And this is the telling point. This is the client's independent metallurgist said, look, it demonstrated that the first pass GEOmet work, or metallurgy test work that was done, effectively was wasted. Now, the cost of the work that we did was about half the cost of that original metallurgy work, okay? If they had had this right from the get-go, straight away that cost, upfront cost, has paid for itself. So, back to the initial slide. Takeaway message is there are a number of comparatively cheap and getting cheaper in terms of 4-acid ICP-MS analyses and spectral analyses that should be integrated and should be collected at the earliest stage in the project. It is comparatively cheap, okay? You need somebody to pull it all together and to communicate that right through the engineers, the metallurgists, the other geologists. You need to build the 3D model and you need to communicate it because it has impact through all of these different applications all through the project life cycle. And overall, if you do this, you provide that critical knowledge early in the project life cycle. You maximise the value, you avoid the opportunity cost of not having done it, and you have that early warning of any potential fatal flaws or opportunities. So, can you afford not to spend a small amount of money up front, get this information, this data, and turn it into information that adds value throughout the project life cycle? So, thank you very much.